in this problem, we want to calculate the mass and the center of mass of the lamina that occupies the region R and has density function rho of x, y. So we're going to do part B. R is bounded by the parabola x equals y squared and the line y equals negative x plus 2. Rho of x, y is a constant. That's nice. It's 4. Okay, so let me show you how I remember these equations once again. So x bar is equal to 1 over the total mass, right? Times the double integral of basically, okay, you got to throw in an extra factor, but it's the density function. dA, what's the extra factor you have to throw in?
Y.
Not for x bar, no. That's why I write it this way. When you write it as x bar equals, it's in terms of x.
So x bar equals I sub y, correct?
You're thinking of x double bar.
Okay.
Yeah, well, that's why it's tough to remember. So this is the formula you want to remember, okay? Now, I will show you this, even though it's not part of this problem. If you want the formula for x double bar, check this out. It took me years to figure this out because books don't point it out. And I don't know why it took so long because it's fairly obvious but after you stare at it, but I never thought about it before. If you make it x double bar, it simply changes the formula by, okay, you put a square on the x and then a square root around the whole thing. There's x double bar. Two symbols different, right? That's how to remember it. Maybe in physics class they do point that out, but they don't in math books as far as I've seen. So I don't know why. And then it's this guy you're thinking of is I sub y.
Yeah.
Okay? And the way you remember that is that's the moment of inertia with respect to the y-axis, and an x values measure distances to the y-axis, right? So that's why it's I sub y. Anyway, none of that is part of this problem, right? So let's erase the x double bar, and that's going to be our formula for x bar, and then y bar is similar. Both of these, and by the way, you're integrating over the region that corresponds with the lamina. So it's a y in here instead of x for y bar. Both of these formulas tell you the same thing. You should find what first? The total mass, which is just the integral of the density function. So that's what you need to find first. And then the beauty of it is that once you set up the mass integral, setting up the other integral is easy. Just multiply by 1 over whatever you get for the mass. And then throw in, if you're looking for x bar, throw in a factor of x in the integral for mass. And then if you're looking for y bar, throw in an extra factor of y. Right? And then that's you got to make these connections. If you try to memorize all these formulas separately, you're going to go crazy.
Wait, you said the density function is
the integral of the density is the total mass of the lamina.
Oh.
Because you're taking the density, which is in mass over area,
Yeah.
and so you're taking the density function, which is mass over area, times the area. So you get mass. So this rho times dA is your mass element. That's one way to remember it. All right, anyway, let's at least find the mass before it's time to go. So the mass, oh, I guess I should draw a picture, darn it.
Rocky Balboa is Rocky Balboa, yeah. The Balboa function.
Okay, x equals y squared, right? And then y equals negative x plus 2. Hopefully that's going to cut this graph of y equals x squared to form a region, right? So that we have a totally enclosed region. So y equals negative x plus 2. What's the y-intercept? 2. So let me draw that in up here. Purple. Okay, there we go. And then the slope is negative 1, right? So down 1 over 1 right there. And I'm not going to, well, let me use my ruler tool. Now, what don't you see? You don't see the intersection point. Why? I just didn't draw it wide enough, right? So it does keep going, and you should realize that. So I need to find that intersection point, don't I? Okay, so let's do that before, let me delete the M. Before we find M, We got to be able to find that intersection point. This one we found by inspection, right? It's 1, 1. This one, so we have x equals y squared, and y equals negative x plus 2. What do we do to find the intersection point? Well, yeah, we've got, maybe it would be best to solve for x in terms of y in this equation. So wouldn't x equal negative 2 minus y, how about? Okay, and then I could plug in 2 minus y right there. So I get 2 minus y is equal to x squared, or y squared, sorry. Does everybody believe that? Let's get everything on the same side. Get 0 on the left side, y squared plus 1 minus 2. Yeah? Okay, I bet it factors. Because your teacher's a nice guy and he wouldn't make you use the quadratic formula unnecessarily. That's not true all the time, though. Okay, so then what? One of them's got to be minus, I guess that one, right? So you set both factors equal to 0. We know about y equals 1, right? That's that value right there. So it's y equals negative 2 we're interested in, and we need the x, well, we don't need it, but let's get it for completeness. What would be the x value that corresponds with that? It's got to be 4, right? You can plug it in there, or you can plug it in there. Either way, you get, in solve, you get x equals 4, I believe. Yeah, 4. So x equals 4. So this would be the point 2, I'm sorry, 4, negative 2. Now, is this region vertically simple or horizontally simple? It's horizontally simple, which means you don't want to use vertical rectangles. So let's use a representative horizontal rectangle. I'll do it down here. So there's your horizontal rectangle, which corresponds to what order of differentials? dx dy. So set up your mass integral, double integral. Rho of xy was just what? 4. 4, and then it's dx dy. And typically you're not as comfortable with this, so get used to setting up that order of differentiation, of integration, excuse me. And then your inner limits of integration will be not be given by the top and bottom of the rectangle, but the left and right, right? So the left of the right, left end of this representative rectangle, the function that touches will give you your lower limit, right? So what would that be? Well, you do have to make sure it's x in terms of y squared. So it's y squared, right? Okay. So lower limit, y squared, upper limit. Okay, it's got to be x in terms of y. We have y in terms of x, but we know that x is equal to 2 minus y from before. So you're going to use 2 minus y for the upper limit. That makes sense? And then for the outer limits of integration, it's with respect to y, right? So the outer integral is with respect to y, so go low to high. So look at this intersection point. What's the y value? Negative 2. So that's, whoops, went too far. So that's negative 2 all the way up to so it's this value all the way up to this value. Now the value of this mass integral turns out to be 18, which means that the value of x bar is 1 over 18 times almost the mass integral, except we throw in an extra factor of x. And so the value of y bar is 1 over 18, 1 over the mass, times almost the same integral, except we throw in an extra factor of y.